Welcome to my classroom. In this fluid mechanics laboratory class, Dr. Raghuram Pandian will explain us determination of viscosity of a given solution using terminal settling velocity data. Ready?
Dear students, welcome back to Fluid and Particle Mechanics Laboratory. Today we are going to do experiment on determination of viscosity from terminal velocity data. At first let me see the experimental setup used to determine the viscosity of unknown solution from terminal velocity data. So in the experiment what you are going to do is you will be provided with two different beads. One is of lead bead, the other one is of glass bead. Two types of beads, one is made up of glass, the other one is made up of lead. In the first one you can able to see that glass beads arranged in the order of bead size, diameter size, ranging from smaller diameter to larger diameter. In the second one you can able to see arrangement of lead beads in the order of size from the lesser diameter to the larger diameter. So let me see the experimental setup used to determine the viscosity of unknown solution using terminal velocity data. So here you can able to see a graduated glass column where the unknown solution is filled in first. Then you would able to find a inlet green mark at the top as well as exit bottom green mark. Students, now we will learn how to find terminal settling velocity using this glass column. At first the liquid is filled onto the top of the column. So you can able to see two markings, top mark is green marking as well as bottom green marking. At first you have to introduce the glass beads from the top of the column, and the beads has to be dropped exactly at the center of the column. This is to be done because the edge effects of the glass boundary on the settling velocity of the glass beads will not get disturbed. And moreover, you will be given some extra liquid height at the top of the column because the entry disturbance for the glass beads in the dropped inside the liquid column, whatever disturbance that is occurred in the traveling of the glass bead within the column will be eliminated. What you understand is that the fluid that enters the top of the column, by the time it reaches the green mark, it will already attain the constant velocity. And moreover, what you have to do is that you have to measure the time of the bead that travels from the top of the
I repeat, we have to drop these spherical shaped beads, glass beads or lead beads or any other beads at the center part of the cylinder so that it won't get deflected or it won't get obstructed in the walls. Okay, so now we will see a demo of how we are dropping this ball. There is a ball we are dropping and you can see that 3, 2, 1, so it starts moving. So it's slowly moving from in the middle, it's not getting disturbed by the wall. Okay, so that way we are performing this experiment. You can see the bead moving here. So with finger we are following it up. You can see that bead is slowly moving down. So from the upper green line to bottom green line, we have to note down the time taken by these glass beads. So that's what we are going to do in this experiment. So now we are going to do the second trial. So our staff Satish is holding the bead in his hand and we are holding it such that it is at the center position of this cross section area in this cylinder, and is dropping the ball. And you can see that once the ball reaches this first green line, we start the stopwatch, and once it goes down, we have to stop when it is crossing the second one. We are showing you in this slow motion. You can see that around 8 you will be watch that one above, just above the green, the bead is crossing. So you have to stop the stopwatch exactly when it is crossing the green line. Okay. So now we'll do another one. So the bead is ready to be dropped, and once if it is dropped, we wait here with the stopwatch. So once the bead comes in, you can see the bead clearly in this one. In this trial, we will be able to catch the bead. So once it's crossed, we start the stopwatch. So as the bead moves down, and once it crosses the second green line, we will stop the stopwatch. Okay. So it is almost taking 8 seconds for the same size of bead which we are doing in this trial 1, 2, 3 and all. Okay. So you can see the bead coming down. You can see it here. So exactly it is going to cross. So once it crosses, we will be stopping the stopwatch and note down the time. So the time divided by distance traveled 1 meter, we will get the velocity. So velocity can be easily determined. This is terminal settling velocity, where the particle is moving with a uniform velocity and it settles down. Okay. Show you 2 more trials. You can see that the bead is going in slow motion. Once it crosses the green line, we have started the stopwatch. So you can observe that bead is moving down clearly in the glycerin solution. So we know the density of this glycerin solution. So now once the bead crosses the second line, we have to stop the stopwatch. So different ball beads will take different time. So here we have a bead which is crossing this green line around 790. So that's what we could able to do. That's why when you do it many times, we are able to closely observe it. So that's why you should not stop with single try. We should do the experiment at least triplicates or 4 times or 5 times as per the time available. Okay, so accordingly you will able to catch the exact time. The average time is taken. Time taken divided distance is fixed, right? So time taken and the distance. So distance travel divided by time will give us the terminal settling velocity. Now you can see this trial where we are able to show it to you in slow motion. The bead is slowly moving. Once it crosses the first green line, we will start the stopwatch. This time we are able to start the stopwatch matching the time it is crossing the first green line. So once it going down, so we have kept some fixed distance. Okay, so we are able to follow that ball in the slow motion video, and you can see that so this ball bead is moving, and once it crosses that fixed distance, we have to stop the stopwatch and note down the time taken. So this one we did it again. So that's why we have to do this experiment 5 to 6 trials will give us an average time taken. So distance is fixed, so we'll get an average velocity taken by the particular size of the bead. So the same can be repeated with the different diameters of the bead and the different material in which the bead is made of. Okay. Well, now Dr. Raguraj Pandian will help explain us the observations and how to do the calculation part, all that, and how to plot the graph. All that will be explained by Dr. Raguraj Pandian. Over to you, sir.
The first aim of this experiment is to determine viscosity of the glycerin solution using the glass beads. In the first case, the glass beads given are known with their density as well as the diameter. The second one, the density of the glycerin solution also will be given to you. So from the experimental part, what you have to do is first obtain the time taken by the glass bead to travel 1 meter within the fluid column. So we know distance traveled and the time taken. So when you divide distance traveled divided by time taken, you will obtain with terminal settling velocity. From the step 1, we have obtained terminal settling velocity, which is nothing but distance traveled divided by time taken by the glass bead in the fluid column. Using terminal settling velocity, we can able to calculate the drag coefficient from this equation. CD is equal to 4 by 3 G into dP, which is the diameter of the particle divided by square of terminal settling velocity into rho spherical bead minus rho F divided by rho F. Rho spherical bead is for the glass bead, density has been already given, and rho F is the density of the glycerin solution. This is also given data. So we know all the data within this part, right hand side of this drag coefficient part. So we can able to calculate what is drag coefficient for the obtained settling velocity, terminal settling velocity. So once you know the drag coefficient, you have to go to standard drag coefficient versus Reynolds number plot. So it will be in this format. What you have to do, you have to extrapolate drag coefficient in that plot, and you have to find out what is the respective Reynolds number obtained. From the respective Reynolds number obtained, you know that Reynolds number is nothing but dP V infinity rho by mu f. So once you get the Reynolds number value from the standard CD versus NRT plot, NRDP is nothing but dP V infinity rho f by mu f. dP is the diameter of the particle, V infinity is the terminal settling velocity, rho f is the density of the fluid divided by mu f is the viscosity of the fluid. So if you see in this NREP, known NREP, the only unknown here is mu f, which is the viscosity of the glycerin solution. By substituting known value of NREP from the standard CD versus NREP plot and dP of given data, V infinity calculated from the terminal settling velocity experiment, and rho f, which is given data. So when you substitute all these things, the viscosity of the glycerin solution can be calculated. So from the previous procedure, we have obtained density of the glycerin solution using terminal settling velocity of glass beads. Okay, now the second aim is to determine unknown diameter of the lead bead using same terminal settling velocity of lead bead. So in this case, the solution given is the same glycerin solution, but in this case, density of the glycerin solution is known as well as the viscosity is known from the previous step. Now a lead bead is given to us, and for which the density is known and diameter has to be found using terminal settling velocity. So to obtain the terminal settling velocity, we know the procedure. What we have followed in step 1 has to be followed here. That is time taken for the lead bead to travel within the glycerin's fluid medium for 1 meter. So if you divide 1 meter divided by time taken for the lead medium to travel at 1 meter, you will get the terminal settling velocity for the lead bead within the glycerin solution. So once you obtain terminal settling velocity for the lead bead, these are the procedures has to be followed to obtain the diameter, unknown diameter of the lead bead. First thing is that, as we know from the equation, drag coefficient equation, CD is 4 by 3 G into dP by V infinity square into density difference between the bead and the fluid divided by density of the fluid. And the next equation is Reynolds number equation, so which is nothing but dP V infinity rho f by mu f. So when I divide CD by NRE, I can get one expression which is explained in number 3. CD by NRP will be equal to 4 by 3 G mu F divided by V infinity Q into density difference between the bead and the fluid divided by square of density of the fluid. So what is the beauty of this equation? So in our case, if you follow this equation, density of the fluid is known and the density difference is known, viscosity of the fluid is known, terminal cycling velocity is obtained from the experiment for the lead bead, and density of the fluid is known. So what are the parameters known here? Mu F, delta density, V infinity and rho F. All these data are known and we can take like CD by NRP as one single constant. From the CD by NRP ratio, whatever parameters on the right hand side are known to us. So we can take all the parameters in the right hand side as one constant, and it can be rewritten as CD by NRP will be equal to constant C. From this relationship, how I can rephrase this? CD will be equal to constant C into NREP. This constant C is evaluated from this equation star. So once I know this analytical expression analytical relationship between CD and NREP, I can assume different NREP. For an example, Reynolds number 1000, Reynolds number 2000, Reynolds number 3000. And I can evaluate what is the corresponding coefficient, drag coefficient for assumed Reynolds number. Say for an example, 1000 Reynolds number, 2000 Reynolds number, 3000 Reynolds number. With the usage of relationship explained before, I can calculate what is CD. So we can calculate CD starting from 1000 NRE with an interval of 1000. You can calculate CD until 20,000. So from the data of NRE CD calculations, you have to plot log Reynolds number NRE, okay, versus log of CD. You have to take log of assumed NREP and log of CD. So if you plot this one, you will get a straight line graph. So with some slope, okay. Then this is from the calculated NRP versus CD. So whatever plot you are obtaining, this is from the whatever assumed NRP and the corresponding CD. You have to take the log of both the things and it has to be plotted. So again, you have to plot one more data in the same graph. So which is the plot that is taken from classical CD versus NRP data. So from any chart, from web resources or from Google resources, classical CD versus NRP plot will be there. You have to extract that CD NRP relationship, and again you have to plot it in log CD NRP plot. So this is from classical
literature.
Standard graph, standard CD versus NRE plot. So this can be standard CD versus NRP plot. This can be obtained from any web resources or any fluid mechanics textbook. So you have to take the log of that standard CD versus NRP data and you have to plot in the same log graph. Okay. Then now you have to find out point of intersection of these two plots. This is calculated, which is originated from the experimental one. So this is originated from standard CD versus NRP plot. Okay. So you take the intersection point and extrapolate to NRE, corresponding NRE. this corresponding NRE, you take anti-log and you can find out what is the NREP obtained. Once we obtain NRP from this log CD log NRP plot, the NREP can be written as dP B infinity rho F by UF. So this is diameter of the lead bead, and V infinity is the terminal settling velocity from the experiment using lead bead, and rho F is the density of the glycerin solution, which is already given, and mu F is the viscosity of the glycerin solution, which is experimentally obtained from the step 1. So from the plot we know NRE. So V infinity from the experiment, mu F from the experiment, and rho F it is given. The only unknown is dP, which is the diameter of the lead bead.
Thank you, Dr. Raghuram Pandian, for the nice explanation. Okay, to summarize what we are doing in this experiment, the objectives are to the first step is to determine the viscosity of a given solution by obtaining the terminal setting velocity data, and second step is using this viscosity data, and we will be determining the diameter of the given metal spherical beads from the terminal settling velocity data. And for this we will be using a cylindrical column. Transparently we can observe what is happening inside that. So we will be dropping the glass beads as well as metal beads in this. So the first step is we will be determining the viscosity of the liquid. Procedure followed is observations we will do. We will determine the density of the glycerin solution using specific gravity bottle. We will take 5 glass beads of uniform size and measure their average diameters by means of a micrometer or Vernier calipers, and we will drop these glass beads one at a time in the column of the liquid, and note down the time taken for the bead to travel from a known distance. We have seen the green labels, right, the top and bottom. How much time it takes to cross 1 meter of the length will be noted down. So that will be the procedure for the first step. In the second step, what we will do is we will take some metallic spheres of uniform size, and we will determine the terminal setting velocity as we are doing in the procedure 1. Okay. So we will observe the distance between the two green markings in the glass tube. So that will be around 1 meter. Write it in terms of centimeters. The density of the glycerin solution, usually we should measure a small amount of mass by unit volume is density. So we will take a certain mass in a specific gravity bottle and we will weigh it. So the volume taken, we know, mass we will take it down from the weighing balance. So we will note down that. So mass by volume will give us the mass density. We will take the given liquid, in this case it is glycerin. We will measure, we will fill these specific gravity bottles are there in 15, 10 ml, 25 ml. We will take one of them. We will say, for example, if you take 10 ml, we will fill this specific gravity bottle with this liquid and obtain the mass. What is the mass of this bottle? We have to first weigh the empty bottle weight. With and without glycerin, what is the mass of this bottle will be determined, and we will subtract the empty bottle weight and to get the what is the mass of the glycerin. So mass divided by the volume taken will give us the specific gravity of the glycerin solution. Okay, so that we can be noted down. We can measure the density of these glass beads. Specific gravity data is given. From that you will calculate the density. Average diameter of the glass beads will be calculated using the Vernier calipers. You have used this Vernier calipers in your physics laboratories in school and first year. So this Vernier calipers will have two type of scales. One is main scale and another one is moving scale, which is Vernier scale. So we will note on the main scale reading as well as the Vernier scale reading, which is called Vernier coincidence. Then we will know for the each instrument, each device, we will have a least square. So in this case, this least square is around 1 by 50 mm, which is 0.02 mm. So here we have 3 glass beads, okay, and 3 lead beads. This is to repeat the things. Instead of single reading, we do 3 readings and we take the average value. Okay, so that way we will use this vernier caliper to determine the beads. Okay, first thing is to place these vernier beads into the vernier, and we have to note down the main scale reading. For example, the main scale reading is for this particular bead is 5 mm. Then note down the vernier coincidence value, and for this bead size the vernier coincidence is 41 mm. Now we will note down these two readings on the paper, and we will calculate the diameter of this bead using the formula diameter is equal to main scale reading plus vernier coincidence multiplied by least count. So this way we will get the diameter of the bead. The same procedure is repeated for the other two balls to get the diameter of the glass bead. And similarly, the diameter of the lead beads of 3 samples will be done using the same procedure, and the data are given in this table. So this is only for representative purpose. So the actual bead that we are going to use for our experiments may be different. So you have to measure your own diameter of the beads. Hello, 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 hello. 3. Okay. So thus using the vernier calipers we will find out the from 3 beads diameter we will take the average diameter of the glass bead for each size. Okay. So for uniform size we will take 3 beads and obtain the diameter using the vernier calipers, and you make use of the average diameter. So thus we have 2.54 mm is for the particular sample. Okay. 3, 2, 1. So as explained by Dr. Raghurashpandian in the videos, we will be taking these beads and dropping them in this cylindrical column and note down the time taken, time of travel, how much time it has taken to cross the given length. Okay, for example 2 green lines are marked, so between from upper green line to bottom green line how much time it took to cross, so that time will be noted down. So we will do it for some 5 samples for the same size, so that average value we can make use of. Okay, so that way 5 times we repeat for the same size of glass bead. For example 2.54 mm glass bead is taken, we will take 5 glass beads of the same size and we will drop them and note down the time taken. So we have time taken as the observation, and the distance is fixed to 100 centimeters or 1 mm 1 meters. So distance divided by time will give us the terminal settling velocity in centimeters per second. So note down the centimeter per second for each sample, each trial using different beads of same diameter. So you can take the average terminal velocity of this thing, and from using the equations, given equations, you can determine the CD value, and from the standard graph we can get the Reynolds number of the particle corresponding value you can get. Okay, so from which again substituting in the equation we will get the viscosity data. All these were explained well by Dr. Raghurashpandian. So then we will move on to the second set of experiments where you will already use the vernier caliper and determine the diameter of the lead spheres. So we have already determined the viscosity of the solution from part A, and density of the lead spheres from specific gravity data we can get it. So now we will take 3 lead beads of uniform diameter and we will measure the diameter in the vernier calipers. So now we will drop them in this cylindrical column and note down the time taken to cross the 1 meter distance. Time taken is noted down. So distance divided by time taken gives us the terminal velocity. Average of these 3 uniform sized dead spheres are calculated. So average terminal velocity in centimeter per second is known. Then using this viscosity value we will calculate the C value, constant value, because we know the density of the sphere, we know density of the fluid, terminal settling velocity we know. So calculate the C value. Once the C value is known, assume NRE value, Reynolds number of the particle value between 1000 to 20,000, and determine the CD value, where CD is equal to this constant value which we determine multiplied by Reynolds value, number value, which is we assume. So after determining these two values, you take log of both the Reynolds number of the particle and the CD, then plot this log of CD versus log of Reynolds number of the particle. And as explained by Dr. Rajaraj, we have to extract the data from the literature graph, or in the textbook you will have CD versus Reynolds number of the particle for spherical shaped particle. So from the graph you take down CD versus NRE value data, then again take log of CD versus log of Reynolds number of the particle, and superimpose the same this data into the earlier plotted graph, and note down the point of intersection. So so once you note down the point of intersection, take the corresponding x-axis value, which is log Reynolds number of the particle. If you take anti-log, we are going to get Reynolds number of the particle, which is nothing but from formula rho Vd by mu. So d is the unknown here, rho terminal velocity v mu. To find the diameter of the lead particle whose diameter was unknown. Here comes the data for performing the calculations. So we have taken a glass bead, and 5 glass beads are taken using Vernier calipers. The average diameter of these beads are found to be 2.54 mm. Okay, so we did 5 beads, and the distance traveled is same for all the 5 beads across the cylindrical column. So time taken for all the 5 beads have been given here. So here the diameter of the lead ball is unknown because we want to determine using the part A result and terminal settling velocity data. Okay, so here 5 lead beads of uniform size is taken, which diameter is not known. Okay, so the distance traveled is going to be 100 centimeters. So the time taken by each bead to cross, remember when we put glass beads, it took some 8 seconds to 10 seconds depending upon the diameter variation. But whereas lead beads, it is a metallic bead, so it took just a fraction of a second. We couldn't even follow it up couldn't even start and stop the stopwatch. It takes only just 2 seconds. So you have to do this very carefully and to get this data. So we have taken a particular diameter of the lead bead, which you are going to determine. Okay, so the time taken is around first sample was 1.85, second sample is 1.87, like that data is given for all 5 trials. So you can calculate the terminal settling velocity for each and take a average terminal settling velocity to do the calculations. Okay, in this laboratory session we have seen how to determine the viscosity of a solution or liquid with using terminal settling velocity data. Also, if viscosity is known, how to determine the diameter of the spherical particle using the terminal settling velocity data on the viscosity determined, right? So there are so many people who have helped us to complete this laboratory experiment. We would like to thank Professor A. Vinod sir. We would like to thank Dr. Rajaraj for his elaborate explanation. We also thank Dr. Sampath Kumar and our ad hoc faculty, Dr. Yashwant, and also we thank our office staff, Mr. Satish. Thank you so much for joining my classroom. Bye bye.